Welcome back to Unit 3 of our course. This is Lecture 9. Now, what I want to do in this lecture is to talk to you about a field of great current interest. This is this field of spintronics, where there's been enormous progress in the last 10-20 years. And what I'll talk about is a very specific aspect in that field, which relates very nicely to what we have been talking about in this unit of the course. Because as you remember, this unit was about these quasi-Fermi levels. That is, the idea that if you look inside the channel, you have an average electrochemical potential, and then there's these two quasi-Fermi levels, one for right-moving electrons and one for left-moving electrons. And the current is related to their difference between the two quasi-Fermi levels. Now, in the field of spintronics these days, there's a lot of interest in something called these topological insulators. And those of you who are familiar with the Hamiltonian, that's how it's written for these materials. But if you're not familiar, don't worry. The main thing this tells you is that if an electron has a momentum k and spin sigma, then the sigma cross k is in the direction of the normal to the surface. So if you're looking at the top surface, for example, for the top surface, y is the normal. So what that means is sigma cross k would be in the plus y or minus y directions. And so if you consider states moving to the right, for which k is in the z direction, then the spin should be in the x direction, so that z cross x is in the y direction. So that's what you could call the upspin, let's say. And similarly, there will be a downspin, which will be associated with states moving to the left. In other words, in these materials, a state moving to the right also has a spin in a particular direction, this upspin. And states moving to the left have a spin in the downspin. And that's, of course, very different from normal materials, where a state moving to the right could have either upspin or downspin. And same true of states moving to the left. Here you have this spin momentum locking. A particular momentum implies a particular direction of spin. So what that means is, I could write the current, which is usually this difference in quasi-Fermi levels, but I could write it as the difference between the quasi-Fermi levels of up and down. And this difference between upspin and downspin potentials, that's what's called the spin potential. And we have defined it with a factor of 2, and that's just a matter of convention. So you could write this as the current as the spin potential times this ballistic conductance. And this factor of 2, that's just a matter of convention. And you could turn it around and write the spin potential as proportional to the current. So the point is that in this class of materials, anytime you have a flow of current, there will be an associated spin potential. One little detail, you see, if you looked at the top surface and you looked at the states, not all of them would have a momentum in the z direction. It would actually have an angular spread in the zx plane. So this is like the zx plane. This is the z direction. And some states will have a momentum that have an x component. But in each case, of course, the spin will be locked to a direction perpendicular to that. So when you add up all the spin potentials, and spin potential is kind of like a vector. So some potentials would be in this direction, some would be in that direction. So when you add them all up, you'd get an angular average. And that's this 2 over pi. But that's a detail. Main point is, in this class of material, current flow gives you a spin potential. How could you measure it? Well, we have talked about how probes measure potentials in the past, where we had a mu plus and a mu minus, and the probe floated to some potential. Now we have a mu up and a mu down, and you could write the conductance associated with the up channel and the conductance associated with the down channel. And if you remember, the principle is The probe is a very high resistance thing, which does not draw any current. And this potential adjusts in such a way that the current flowing in here is exactly equal to the current flowing out here. That is, if you write these two currents, two inward currents, they add up to 0. Right? And based on that, you could usually write the probe potential in terms of up and down. Now, ordinarily, what would happen is G up would be equal to G down if you had an ordinary probe. And then mu p would just be half of the sum. That's like the average of the two. But if you use a magnetic probe, let's say a magnet that points in the x direction, then one of these conductances will be much bigger than the other. That's again another important development of the last 20 years in this field, which is the basis for a lot of useful devices, where it is clearly established that a magnet pointing in a certain direction has a relatively low resistance contact to spins in that direction. And so G up could be much bigger than G down. And then the actual probe potential would be again a weighted average of up and down, and the weighting depends on these two conductances, up and down. Now, the important point is that if I can easily reverse the direction of a magnet. And if I reverse the direction of a magnet, then you see up and down get interchanged. And so the probe potential should change. That is, instead of G up here, I'll get G down. Instead of G down there, I'll get G up. And so you'll have a different potential now. Because previously, let's say it was 90% of this and 10% of that. If I reverse the magnet, it will be 10% of this and 90% of that. And so if you look at the difference in the probe potential, that is, with the magnet pointing in one direction, I get a certain potential. With the magnet reversed, I get another different potential. And if I look at the difference will be a measure of this spin potential. And multiplied by this quantity here, which depends on how different the two conductances are. See? And that is usually what's called the polarization of the magnet in this context. So this is now a standard way actually of measuring spin potentials. That is, measure the potential with a magnetic probe, reverse the direction of the probe, and see how much it changes. If it's a non-magnetic probe, of course, you shouldn't get any difference here. Or if there is no spin potential, then when you reverse the magnet, there will be no difference in what you measure. But if there's a spin potential, then you should measure this difference. And so you could write then, as the measured difference, what you're actually measuring would be like what we had times this polarization of the magnet. That is how effective your probe is in measuring this quantity. So this part is kind of the intrinsic spin potential. This kind of tells you what you'd actually measure with a probe. And it depends on the polarization of the magnet. And this other quantity I've introduced, that's like the property of the channel, which so far actually in our discussion is 1. And what I'll next explain is how, in general, it could be less than 1. Let me get to that point. So far I talked about these topological insulators, where you have this perfect spin momentum locking. That is, if a state is going to the right, it has a spin in a particular direction. Whereas you have these non-magnetic materials, the ordinary materials, where usually, if you're going to the right, you could have an upspin or a downspin. Now, in general, though, there's a lot of materials which have spin-orbit coupling. And in general, anytime you have spin-orbit coupling, you have a situation like this, where you have right-moving states, left-moving states. You have up states, and you have down states. So in general, there's this 4 combinations. Right moving up, right moving down, left moving up, left moving down. Now, usually what you expect, this is generally referred to as time reversal symmetry, that if on a highway you have 50 lanes going to the right, there should also be 50 lanes going to the left. Of course, they don't have to be filled with cars equally when they're out of equilibrium. One side could be more filled than the other, but as far as the lanes are concerned, there should be, if there's 50 to the right, there should be 50 to the left. Now, that's not really the most general situation. In materials with spin-orbit coupling, which have this time reversal symmetry, if there's 50 lanes, 50 upspin lanes going to the right, there should be 50 downspin lanes going to the left. Similarly, if there's, say, 40 downspin lanes going to the right, there should be 40 upspin lanes going to the left. So in other words, these two must have the same number of lanes. These two must have the same number of lanes. But fundamentally, there's no reason why those two have to be equal. And depending on the strength of this spin-orbit term, m and n could be widely different. Of course, normal materials are where m is equal to n. That's what we are generally used to. But m can be very different from n. And of course, an extreme example is these topological insulators where n is actually equal to 0. So right moving means upspin, left moving means downspin, because n is 0. But more generally, n is not 0, and you could define this polarization as m minus n over m plus n. That's the p that enters here. So you'd still have a spin potential as long as m is different from n, but it would be somewhat smaller because of this factor. Now, these are details that's in the notes. I'm not going into it because, as I said, this is a little bit of a detour from the main topic. But main point that I really wanted to get across in this unit is this concept of quasi-Fermi levels. The idea that different classes of states could be occupied differently, and hence you could have different electrochemical potentials or quasi-Fermi levels. So much of this unit, we have been talking about the difference between right-moving states and left-moving states, and how they can have different quasi-Fermi levels. In the field of spintronics, it has become quite common to talk about the spin potential, the difference in the quasi-Fermi levels for upspins and downspins. And as we move into new materials, especially with spin-orbit coupling, and we talk about ballistic conduction and so on, more generally, you see, we should have 4 quasi-Fermi levels because there are 4 types of states. There's upspin, downspin, right moving, left moving. So there's 4 combinations, and each one could have a different quasi-Fermi level, you see. And this is, of course, very hard to describe if you take the attitude that, quasi-Fermi levels are complicated things, confusing things. Let's just stick to electrostatic potentials. Well, if you just stick to electrostatic potentials, you're missing a lot of rich physics. That is the real mess. I've made other reasons why electrostatic potentials may not be very useful because of how they smear things out. I've made that point before. But right now, the main point I wanted to drive home is, as the field of nanoelectronic devices develops, and you look at newer and newer devices with all kinds of contacts and materials with which you're able to control different types of states, you'll get into situations where there'll be multiple quasi-Fermi levels. Just as in biological systems, you have different potentials for, say, potassium ions and sodium ions. So you'd have this rich physics coming out of different types of quasi-Fermi levels. And in order to understand all that, it is really important to get beyond this mindset of using electrostatic potentials to understand current flow. It is really these quasi-Fermi levels that are more fundamental and more central. So that sort of brings us to the end of the topics we wanted to talk about in this unit. And now it's time to sum up. And that's our next lecture. Thank you.